Good afternoon. I'm Norman Wildberger, and we're talking about Lecture 6 in this course on History of Mathematics. We're going to talk about polynomial equations today. So we've been talking about the ancient Greeks, we've talked about the Chinese, Indian, and Arab cultures, and now it's time to turn our attention to Europe. And in particular, there was a kind of a golden age of European mathematics. Started around 1400, but I guess really kicked in around 1500 to about 1900. So a golden age of European mathematics, which no doubt rivals in creativity and in brilliance the work of the ancient Greeks. So we have to talk a little bit about the setting here. In the medieval period, Europe was a little bit of a backwater intellectually, although there were some important things that were done. It was perhaps not such a backwater as people sometimes imagine. Certainly the Gothic cathedrals are strong evidence that there was a very sophisticated building culture, and technology was in fact rather well developed. But overall, in terms of sort of abstract development of science, it lagged behind. And there were a couple of critical sort of setbacks to, or maybe setbacks or difficulties that prevented Europeans from fulfilling their potential, say, in the medieval period. So in particular, for example, there was there were crusades. To the Middle East that occupied a lot of energy and time. There was a plague, Black Death, around in the 1300s. The influence of the church was a little bit of restraining influence. The mentality of the time before this age was very much towards salvation and scripture, and independent thought was a little bit hard to get going. What else? There was a lot of political instability, a lot of little kingdoms battling each other, lots of wars constantly. So there was not a uniform political structure. So all of those things and others contributed to sort of a low point in European history. But then around 1400 to 1600, things started to pick up. And this period is often called the Renaissance. Renaissance, and it's a period of the beginning of a kind of explosive growth of creativity. So some of the contributing features to this development were, well, certainly there was the Arab influence, bringing culture and, especially in mathematics, bringing translations of Greek works, and also the Arabs' own scientific developments that were quite valuable. And a lot of this Arab influence came via the Moorish settlement in south of Spain. So there are the great Islamic cities of Cordoba and Seville and Granada that were established in south of Spain that sort of provided a bridge to Europe. There were also Jewish merchants that played an important bridge between Arab and European influence. Also, around that time, there was another culture around that we haven't mentioned because they didn't figure too prominently in the development of mathematics. This was the Byzantine culture, which was centered around Constantinople, which is present-day Istanbul in Turkey. And when the Roman Empire split up, the church divided into two. There was a Roman church and then an Eastern church, which was centered in Constantinople. And the Eastern church was Greek in language and culture. And so this empire, known as the Byzantine Empire, lasted quite a long time. And it preserved the Greek works. So they were rather important in preserving the Greek works in the original Greek. And around the 1400s, the Byzantines were in conflict with the Turks, who were moving into that area, and they appealed to the Italians for help. So there was some strong connection between the Byzantines and the Italian city-states, which were the most prosperous in Europe at the time. So there was a connection there. So we have the Arab influence, we have the Byzantine records, but we also have a growing independence of thought and a questioning both of, well, church doctrine, but also of earlier scientific framework that had basically been taken from Aristotle. So Aristotle is not really a mathematician, but he was a philosopher in ancient Greece who outlined a broad framework for science. And okay, a lot of the things that he believed in are not quite right or are openly wrong, but nevertheless they formed a basis for scientific thought. And people started to realize that there was problems with Aristotle, and they started openly challenging it and thinking about alternatives. One of the important ideas of Aristotle was that velocity, the movement of a particle, was the result of a force. So, for example, he believed that velocity depends on a force. So he taught that nothing moves unless there's a force pushing on it, and the stronger the force is, the faster the velocity is. So that turns out to be substantially incorrect, even though intuitively it's not too surprising. It seems to sort of correspond with what we see. But Newton ultimately showed that this is not right. It's the acceleration that depends on the force, not the velocity. And there's a very key difference. But anyway, that's what kind of example of Aristotle science that people were moving away from. And of course, there was the split in the church. The church became a little bit less powerful. We have a split. So in England, we have the Church of England going its separate ways. And then in the Reformation, the establishment of the Protestant side of the church, and that provided a counterbalance to the Roman Church and allowed somewhat greater flexibility of thought. Okay, another important influence around this time was that finally the Hindu-Arabic number system was accepted, and that was a big driver to the development of science. Okay, so now let's turn to mathematics. Who were some of the figures? What were some of the developments there? There was increasingly an idea that nature was controlled by laws that were essentially mathematical. In origin. For example, Galileo lived around 1500, 1600, that period. He said, "Nor does God less admirably reveal himself to us in nature's actions than in the scriptures." Nor does God less admirably reveal himself to us in nature's actions than in the scriptures. So he's expressing the idea that we can find God in the scriptures, yes, but we can also find God by looking out in the real world, in nature, and seeing what's going on there. That's also a manifestation of God's work. And that kind of thinking was shared by a lot of mathematicians who saw the beauty of God in the mathematical patterns they discovered. Okay, another very important development is the introduction of new symbolism. To go along with the Hindu-Arabic number system, we had a lot of new signs that we didn't have before. And so instead of having to write out long, complicated equations in terms of words, we could write them out compactly using symbols. So for example, the plus sign that we all know was introduced by Oresme in the 1300s. The minus sign was introduced by Widman in the 1400s. The equals sign was introduced by Ricordi, 1500s. Multiplication by Oughtred, about 1500s. The less than, greater than signs by Harriot. I think that was also 1600s. Our term for infinity by Wallace in the 1700s. And a very important contribution by Frenchman Vieta, or sometimes pronounced Viete. I guess there's an accent here. Francois Viete, who was the leading mathematician of the 1500s. Very importantly, he was the one really who introduced letters for indeterminates or unknowns. Such as X and Y. Descartes, who plays a major role in the history of mathematics, is also 1500s, 1600s. He went a little bit further than Vieta and introduced the idea that unknown constants are generally represented by letters from the beginning of the alphabet, like A, B, and C, while unknown variables usually represented by letters at the end of the alphabet, like X, Y, and Z. So you can see this is a great number of very important symbols that really were only words often to express them before these mathematicians started using them. While I'm on the subject of notation, I'll mention a few other things, some of them that came later. But the notation for powers, like x cubed and y to the fourth, that was certainly being used by Descartes in the 1600s, who also coined the term imaginary numbers for complex numbers like I. Newton, in the 1600s, used fractional powers like x to the 5/3, and also used negative powers. Surprisingly, x squared alone, Gauss only in the 1800s finally replaced xx with x squared. So the power x squared held out long after x cubed and y to the fourth were being used. People were still writing xx for x squared. The symbol for pi that we use was due to Euler in the 1700s. And he also introduced I for our imaginary number whose square is -1. He introduced this for summation, and he introduced our functional notation f of x. So in these years, a great new inventory of signs allowing people to write things a lot more concretely than before. This fellow Vieta, who of course is rather important because this is a very important idea to introduce actual letters for indeterminates instead of words. He was also famous for having broken a code. He was one of the world's first code breakers. France was at war with Spain, and the King of Spain would send coded messages, and somehow Vieta was able to decipher these codes and so give the French some kind of military advantage. All right, so these are some of the tools that the Europeans had. And now let's talk about a subject that was very important in the early stages of mathematics in the European story, the story of polynomial equations. Solving equations in unknowns. So the most important example of such a thing, well, after the linear example, I suppose, which everybody knew about, is the story of quadratic equations. And most of the ancient cultures knew how to solve quadratic equations, so the quadratic formula that we all learn. And often it was expressed in the following way, that if you have two numbers, x and y, and you know what their sum is, and you know what their product is, then what are the two numbers, x and y? Well, that would have been expressed in terms of the equation x squared plus q equals px. Today we would rather write x squared minus px plus q equals 0. But the ancients were quite wary about subtraction because they worried about negative numbers. Okay? If you're subtracting, then you can get negative numbers, and then what do? So they typically try to rearrange equations so that there are always only plus signs involved. So the ancients often thought about a quadratic equation as having different forms. There wasn't just one quadratic equation, there were a lot of different quadratic equations depending on the signs of these numbers here. So if this one was negative, you'd have to put this one on the right-hand side to make it positive. If these were both negative, you'd have to put them both on the right-hand side to make them both positive. And so they had sort of different rules for the different kinds of quadratic equations. The quadratic equation formula that we all know was probably first written down by Brahmagupta. And Al-Khwarizmi perhaps gave the first geometrical interpretation of it in terms of completing a square. So Al-Khwarizmi, the idea of completing a square. And let's illustrate that with an example. Suppose we want to solve x squared plus 10x equals 39. So he said, all right, what we do is we think of a square, and we think of, say, that being x, and that x, so that's x squared right there. So that's that term there. And then 10x, we'll think about that by adding a segment of length 5, which is half of the 10. And then that's 5x, and that's also 5x for a total of 10x. So he said, all right, what we have to do is we have to add something else to make a square. In this case, how much do we have to add? Well, we have to add the area of this square, which is, of course, 25. That's completing the square. So what we do is we take x squared plus 10x, and we add 10x, and we add 25 to both sides. And now what's over here is a square. It's x plus 5 squared. And over here we have 64. And so if a square has area 64, then its side must be 8. So x plus 5 must equal 8. And so x equals 3. These days, of course, we know that there's another solution, because we could also take x plus 5 equals minus 8. So the other solution, x equals minus 8 minus 5, or minus 13, was not in the picture for him or for the Hindu mathematicians either, or for the European mathematicians either. So this was not geometrically valid. First of all, what was a negative number? What does it mean to have a square of size minus 13? Okay, so that was not considered. There was only one solution. So when you solve a quadratic equation this way, the key step after the completing of the square is to take the square root of the right-hand side. Right? So you need to be able to take a square root. So for example, if I just make up a number, if I just take 6,253, and I work out what the square is, whatever it is, and then I give that number to you and ask, what's the square root of that number? How are you going to go from that number to 6,253? Well, you could do trial and error. You could try something 6,000. You could try 7,000. You could narrow it down. But there was a systematic method. There were several systematic methods that historically were used. And they're important. You can tell when one of these ideas is important because it developed in a lot of different cultures. So the ancient Chinese knew how to complete a square. The Babylonians were interested in it. The Arabs, the Hindus. Everybody knew that having a method for finding a square root was an important mathematical tool. And the earliest way of finding a square root goes back to the Babylonians. So how did the Babylonians solve x squared equals n? So we're given n, we want to find x. Well, what they did is they say, all right, take a guess. Let's say x1. And then what you do is you compute x1, you compute n over x1. Now, if your guess is less than the square root, then this is going to be bigger than the square root. And if your guess is bigger than the square root, then this is going to be less than the square root. So they said, all right, so now take an average. The average, say x2, is x1 plus n over x1. That's going to be your new guess. That's your, is the new guess. And repeat. Now you iterate. A long time later, Newton introduced a very general way of finding a zero for any equation, or any polynomial equation, say. And when you apply it to something like this, his method amounts to this. You look at the equation x squared minus n, and geometrically that's some kind of parabola. And Newton's method for solving or finding a zero, let's say you want to find one of these zeros, was to start with a guess and to compute the tangent to the curve at that guess. And where the tangent meets the x-axis is the new guess. So the next iteration, you would go up here and take a tangent, get the third guess. So it turns out that for a quadratic, Newton's method equals the Babylonians. But there's a little bit of a problem with this, namely that if you're actually doing it for big numbers, you have to do this division, which is a bit painful. So there are other algorithms developed, and I'll just mention a more modern algorithm. Sometimes called the Vedic method. So it was discovered by the Indians. And it's a sort of a step-by-step procedure for obtaining the decimals digits of a square root. It's a little bit too elaborate for me to describe here, but if you're interested in that, I have a video that describes it. So in my Math Foundations series, Math Foundations 49, it's called How to Find a Square Root. You can see how the Indians' method works. Now the Greeks would have said, but wait a minute, we know a much better way of taking a square root. So the ancient Greeks thought entirely geometrically, not arithmetically. And they would have said, you do the following. If you want to solve x squared equals n, you should first of all think whether n is bigger than or equal to 1. Suppose that, case 1, that n is less than 1. So you draw a line segment of length 1, and then on here you make a segment of size n. And then at the center of this line segment, you draw a circle. So this is a diameter. And you go up here, and then you look at this quantity x. So this is a right angle by Thales' theorem. So we have some similar triangles. So this side to 1 in the big triangle is equal to n over x in this littler triangle here. And so x squared equals n. So geometrically, finding a square root is relatively simple. It's a simple ruler construction, but arithmetically much more difficult. What happens if n is bigger than 1? Well, then you just interchange the roles of the n and the 1. So you start by having a diameter of size n, and then you make a 1 here. And otherwise you do exactly the same thing. And then for the same reason, that x there will be square root. The same argument. Okay, so quadratic equations had been studied for a long time. What about cubic equations? Well, the simplest kind of cubic equation is one that looks like this, where you're trying to find the cubed root of something. X cubed equals n. And Omar Khayyam had a way of thinking about that. He said, let's think about two curves. Let's think about y equals x squared, which is a parabola. And let's think about replacing the x squared here with a y. So that becomes y times x equals n. Well, that's a parabola. And that's a hyperbola. So if you graph them, which he didn't do. Well, he did, but not with the coordinate system like I'm doing now, but he did have a graphical representation. So you have a parabola for y equals x squared, and then y times x equals n is some kind of hyperbola like this. Actually, the hyperbola has another branch outside here. And where the two meet, there's an x-coordinate. And that x-coordinate, if this equals this, then if you just substitute this into here, then x cubed will equal n. So this must be the cubed root. Of course, this construction is not a ruler and compass construction, because you can't actually draw the graph of a parabola or a hyperbola with a ruler and compass. With a ruler and compass, the only things that you can draw are circles and straight lines. You can draw as many of them as you like, but you can't actually draw any other curves. So this is, strictly speaking, outside the framework of the Euclidean construction world. But nevertheless, it's an example of a cubic equation being solved geometrically. A natural question is, can you find, say, the solution to x cubed equals 2? Can you find that somehow using ruler and compass? Maybe not in this way, but in some other clever way. And the answer, as it turns out, is no. And Euclid probably had a sense of this, but it took the Europeans to eventually figure out what was going on. And what eventually is the story is that Euclidean constructions using a ruler and compass allow you basically to only create square roots. And rational operations with a ruler and compass. So for example, you can create something like square root of 1 plus square root of 5. That you can do with a ruler and compass. But a cubed root or a fifth root or pi or e, those numbers, as it turns out, are beyond construction by ruler and compass. And there's a very nice set of problems in Stilwell, okay, in chapter 6 that discuss this rather important point. What exactly you can do if you start out with rational coordinates and you're only going to take straight edge construction between 2 points, or drawing a circle with a particular rational point and a rational radius. What can you do? Well, basically, you can only end up constructing things that are arithmetically formed from rational numbers by taking square roots and possibly repeated square roots. Square roots of square roots of square roots. You can do that, but that's all you can do. So I think it's a very nice set of problems there. They're all consecutive, so I'd like you to have a look at them. So I think problems, I think the next one on our list is 13. So problems 13 to 18 are in Stilwell. Problems 6.3.1 to 6.3.6. So starting with rational points in the plane, ruler and compass constructions yield only rational numbers and square roots. So that's the basic aim of this series of problems, is to show that starting with rational points in the plane, ruler and compass constructions yield only rational combinations and possibly nested square roots. Okay, so now our story moves to the Europeans, and the Europeans also tackled the cubic equation. So the general cubic arithmetically. This is a holy grail for 16th century mathematicians, and there are a number of names associated to them. Tartaglia, Cardano, Del Ferro, and there's probably a few others. So these were Italian mathematicians, and they were tackling the following question. You've got some cubic equation, x cubed plus ax squared plus bx plus c equals 0, an analog of the general quadratic equation, and what you want to do is you want to find a formula for the zeros in terms of a, b's, and c's, and in terms of square roots and cubed roots. So you want a formula just like the formula for ax squared plus bx plus c equals 0, where x equals minus b plus or minus square root b squared minus 4ac all over 2a. That formula for the quadratic equation, which essentially goes back to Brahmagupta, is the inspiration. Okay, so they wanted to find a similar kind of formula for this cubic. They've divided by the coefficient of x cubed here, so that's 1 to make it a little bit simpler. So we want a formula like this involving what? Well, involving square roots and cubed roots. And this is a favorite topic in the history of mathematics because these various people involved here were rather colorful characters, and it was an interesting period of time, and there's a rather sordid story in terms of claiming credit for the discovery of this. Okay. Probably the credit should mostly go to Tartaglia, who was called the Stutterer, because when he was a young lad, the city that he was living in Italy was subject to a siege by the French forces, and some French soldier came in and cut his face with a saber. So he had his jaw was cut, his face had a big scar, and he wasn't able to talk quite properly. And okay, so that was his name, and he was a very brilliant fellow, I think. But he discovered this formula first. And Cardano and others had been working furiously on it. Everyone wanted to find this. And Tartaglia found it, and they would challenge each other to contests. Like you would make up a cubic and ask the other person to see if you can solve this cubic. And if they didn't know how to do it, they wouldn't typically be able to find it, because if the numbers are big enough, it's hard to find using trial and error. So it was clear that Tartaglia knew it, and Cardano pleaded with him to tell him, and said he promised that he wouldn't reveal it to anyone else. He just wanted to know. So Tartaglia reluctantly told Cardano, and then Cardano promptly wrote a book in which he divulged the secret and claimed it more or less as his own, at which Tartaglia was very annoyed, of course, and there was a long-standing battle for priority. So what is this method? So let's have a look at the method. So what we do is we start with this equation here, and first we make a substitution. We replace x with y minus a over 3. This is the analog of completing the square in some sense. What it does is it gets rid of the x squared term. Okay, if you replace x with y minus a3, you get a new cubic, and if you write it all out, you'll see that there's no more quadratic term. So you get a new cubic, which has the form, cubic now in y, which has the form y cubed equals, and we'll write it py plus q. And p and q depend on an obvious way on a, b, and c. And so we can just now concentrate our efforts on solving this. And once we've solved this by the substitution, we can solve that. OK, so what is the trick? Well, the trick is to let y be equal to sum u plus v. You introduce two sort of dummy variables, u and v, and you suppose that y is equal to u plus v. Then the left-hand side of this equation, once you cube it, it will be u cubed plus v cubed plus 3uv times u plus v from the binomial theorem. It's 4 terms with coefficients 1, 3, 3, 1, and you can group them in this fashion. And since u plus v is y, we can write this as u cubed plus v cubed plus 3uvy. So that's what y cubed is. And we want to arrange that this right-hand side be p times y plus q. So we want to arrange that p is equal to 3uv and that q equals u cubed plus v cubed. So we know p and q. We're trying to find u and v that satisfy that. Well, that's not too hard now, because we can replace one of these with the other one, substitute one into the other. So we can get u cubed plus p over 3u all cubed. So I'm replacing v with p over 3u. And all of that cubed is equal to q. Now that is a quadratic equation in u cubed. If you just think of u cubed for a second, it's like this variable plus 1 over that variable cubed. Okay, it's like that variable plus something over that variable is something else. That's a quadratic equation in u cubed. A quadratic equation in u cubed. Well, we know how to solve quadratic equations, so we can write out what that quadratic equation gives us for u cubed. So maybe I'll write it sort of like z plus p cubed over 27z equals q. That's the kind of quadratic equation where z is u cubed. Okay, and what do we get when we do that? Well, we get u cubed equals, okay, you have to do a bit of arithmetic here now, but basically the quadratic formula gives us q over 2 plus square root of q over 2 squared minus p over 3 cubed. Now that was u cubed, but the same argument applies to v cubed. So v cubed should also have that same form. So also v cubed should equal q over 2 plus or minus square root of q over 2 squared minus p over 3 cubed. That's v cubed, sorry, v cubed. We still want to guarantee, however, that u cubed plus v cubed equals q. So when we add these two together, we should get q. And that means that one of these should be a plus sign, and the other one should be a minus sign. And it doesn't really matter which one we call plus and which one minus. So since u cubed plus v cubed should equal q, we get that u cubed actually should be q over 2 plus, say, q over 2 squared minus p over 3 cubed. And v cubed equals q over 2 minus square root of q over 2 squared minus p over 3 cubed. And so finally, to get y, we need to add u plus v. And so we should take the cubed roots of these expressions. Since that's another thing we're allowed to do, right? We said we're going to allow cubed roots and square roots. So we get cubed root of, say, u, which is q over 2, plus square root of q all over 2 squared minus p over 3 cubed. So there's a cubed root of something plus a square root plus another cubed root of the same kind of thing but with a minus sign instead. Q over 2 minus the square root of q over 2 squared minus p over 3 cubed. Now, in previous courses, students were made to memorize this and to apply it in a few examples. I think the reality is, if one is honest, that this formula is a lot less important than Cardano and Tartaglia thought it might be. This did not end up being a holy grail to algebra. In fact, it was a little bit of a dead end. You can certainly, with some more trickery, you can do the same kind of thing for a quartic equation of degree 4. And that's even a little bit more complicated. But it turns out that that's as far as you can go, that there's no corresponding thing for a quintic equation, but not for higher degrees. This was only realized later. So that's one way in which this is a limiting thing. I'm a working mathematician. I've been making computations for decades and decades. I've probably used this formula a couple of times, and invariably whenever I use it, I'm a little bit disappointed with what you get. It's complicated. It just ends up being not that useful. And there's a little bit of a complication that sometimes what's inside here can be negative. Right? We're taking the square root of something. So sometimes you need to go to complex numbers even when you know that your cubic has a 0, because all cubics have zeros. So this is a kind of an embarrassing thing that Cardano and realized, that somehow you needed complex numbers to make sense of this. And once you've got complex numbers, then you have to worry a little bit about the cubed root, because then there are 3 possible cubed roots. You have to be a little bit more careful choosing this cubed root and this cubed root in the right way. Okay, so it's a little bit complicated, but it's just a formula that's not very used very much, because it turns out that the quadratic equation is just 1,000 times more important than this cubic equation. The quadratic equation is used all the time because it's intimately connected with geometry. But the cubic equation is not really very important. Cubic equations and cubic curves are important, but the problem of finding their zeros is not that critical. So maybe it's a little bit of a disappointment, but it turns out that Tartaglia discovered something else also, which is perhaps even more remarkable. So I'll tell you, we'll take a break and then I'll tell you what that is.